And welcome back. Let's jump straight into Model 4 from Chemical Activity 9, where we're looking at the critical thinking questions. And here we are now with Model 4. Again, we've seen this before. And we look at the first question. What is the experimental value for the electronic energy of helium? So this is the true measured value, referring us back to the earlier models. Part B are the average energies for the trial functions with z prime equals 2, or for the trial function with z prime equals 27 over 16. Are these higher or lower than the experimental electronic energy of helium? We're going to find that both are higher. So you just do the comparison, and they're higher because of this. They're actually less negative, so they're higher values. Which is the better trial function? Well, it seems that the best trial function is the one with z equals 27 over 16. Why? Because it yields a lower energy, and that's what we care about for our variation method. Question 15 now is getting us to refer back to the models that we've seen. We're told that electron 2 is closer to the nucleus, and we're told that electron 2 is starting to screen the nuclear charge from electron 1. In both cases, both electrons are in the 1s orbital, and we're asked, do we think that electron 1 can screen the nuclear charge from electron 2? So my answer is kind of, well, intuitively, the electron 1 is actually further away from the nucleus. But we also know that the electron is not a single particle that sits in one particular position. Again, quantum mechanics tells us about probabilities. So there may be some screening, but this question here prompts us to think a little bit. It's not so certain when we're dealing with quantum mechanics. In any case, we're prompted to think in question 7 about why the trial with z prime being 27 over 16 gives a better energy value than when z is equal to 2. And the key here is that 27 over 16 is less than 2. So that means that really each electron actually is shielded a little bit from the nucleus. It doesn't see such a large positive charge as the one that actually exists there. It's as if the repulsion between these electrons forces one to always be impacted by the other. So I'm writing here that the lower value here takes into account some kind of screening. Now we're given some more information. We're introduced to the term effective nuclear charge. This term shows up in our general chemistry textbooks, so it's nice to connect back to that. We're also told that, hey, guess what? We can have a trial function with 2,000 parameters, and we start to get much, much closer to the true energy value, to the true experimentally determined value when we get functions that get more and more complicated. Of course, there's a trade-off. The more complicated the function, the longer that it takes to do the calculations. Of course, this is why computers have been so valuable for moving us forward in terms of quantum chemistry. And now we start to look in Model 5 at lithium. And so with a lithium nucleus that has a +3 charge, but now we've got 3 electrons to think about. So we're going incrementally more complicated from the helium atom, and we still can't solve the Schrödinger equation for the lithium atom. We're given some more information from photoelectron spectroscopy about the different energy levels for the electrons, but we're also introduced now to a new trial function, and we might start to think about what the best choices for that trial function are. In this particular case, we've got psi1s, psi1s, and psi2s. That makes some sense to us, again, knowing what we know from general chemistry. The questions we're now asked to consider are ones about how we might make up the Schrödinger equation. And so we start, of course, with the classical physics of the system. So how many kinetic energy terms would we expect to be present? Well, we think there'd be 3. There'd be 1 kinetic energy term for each electron. How many attractive Coulombic energy terms would there be present? Well, again, we'd expect 1 attractive Coulombic energy term for each electron, because each electron would see the nucleus. And then how many repulsive Coulombic energy terms are present? Well, now we've got an interaction between electron number 1 and electron number 2, electron number 1 and electron number 3. and electron 2 and number 3. So we'd expect 3 repulsive terms. So our Schrödinger equation is clearly going to get much more complicated. And indeed, if we try to take all of these terms into account, we're going to have 3 kinetic energy terms for the electrons. This is where we see these del functions in here, del squared functions. We're now going to see some attractive terms. We know they're attractive terms because they've got negative charges in front of them. It's because we've got the charge on the nucleus, which is positive, multiplied by the charge on the electron, which is negative. And then we have these repulsive terms in here, and as we just described, there are 3 of those repulsive terms. So that's the Hamiltonian operator. It's operating on the wave function, and in our Schrödinger equation, of course, we end up with the eigenvalue, the energy multiplied by the wave function. Model 6 asks us to think about screening once again, and this idea of the effective nuclear charge. Critical thinking question 21 again asks us to start to sketch a diagram where we have these electrons shield the other electrons from the nucleus. And critical thinking question 22 also asks us to sketch a diagram where now electron 3 screens electron 1 or electron 2. These are critical thinking questions after all, so they're encouraging you to think about what we're looking at. So given our current understanding, based on the trial function, we've got electron 1 and electron 2 with psi 1s orbitals, and we've got electron 3 going into a psi 2s orbital. We're asked to explain why the configuration where electron 3 is closer to the nucleus, why that configuration is less likely. And of course, because we already recognize from general chemistry that the psi 2s wave function, and we've seen this in the radial distribution function. So psi 2s we recognize to be further from the nucleus. We also recognize, of course, that this is probability, so it is possible that the electron could be closer, but it's less likely. And again, we've got this smearing out of the electron based on what we think the probability density is telling us. Critical thinking question 24, again, lives up to its name. So to some extent, every electron shields the nuclear charge from every other electron. This is true because we have a smeared out electron. We have effectively the electron being the square root of a probability density. That's the wave function for that electron. It's helpful, though, often to think about radial probabilities, and we'll come to that shortly. And now we get to question number 25, and this one requires a little bit of thought. So what are we asked to do here? We're asked to compare the shielding between psi 2s and psi 1s with the shielding between psi 2p and psi 1s. And the way I like to think about this is if we look at that 1s electron density, we look at this probability density. This electron is very firmly held at this region of about 54 picometers away from the nucleus, the Bohr radius. And if we look at the 2s orbital, there's some significant probability that that electron in the 2s orbital is also very close to the nucleus. It's not shielded as such from that nucleus in this particular region. When we compare the 2p electrons, an electron in a 2p orbital, we see that effectively the shielding that would take place from this 1s orbital would be in this region in here, and this shielding effectively would probably push that 2p electron a little further away from the nucleus. The electron in the 2p orbital would probably more likely see the electron in this 1s orbital, and therefore not be as well connected to the protons in the nucleus. And so this final critical thinking question, 26, it asks us to reflect on our answer above. And we're trying to explain why the ground state of lithium is 1s2, 2s1, and not 1s2, 2p1. And this is basically, if we think about this, that 2s orbital is not so shielded from the nucleus. Therefore, the electrons are going to be more attracted to the nucleus. They're going to drop into that 2s orbital. There's going to be a lower energy configuration there because of the force of attraction between that electron and the nucleus. If we put the electron into the 2p orbital, then there's a shielding. We're going to have that outer electron see more of a repulsive element from the electrons in the 1s orbital. So have a think about this. We definitely know there's going to be a lower energy because of the attraction with those electrons in that 2s orbital that kind of overlaps with the 1s orbital. It has electrons being closer to the nucleus, and that's what the electrons want to be able to do, get closer to that nucleus. So thanks for listening to this. Have a think about it. Some good questions in this particular exercise. Keep thinking.